else? Okay. Do you have any questions, first of all? Yep. Yeah. They are necessary for the formalism, and there will be maybe an additional interpretation in the next chapter when we discuss unitarity. So in a way you can see that ghosts must appear in Feynman diagrams with interactions in order to correct the imaginary part of the S matrix elements. With the ghosts in the Feynman diagrams, the imaginary part becomes correct. Without the ghosts, the imaginary part becomes wrong. The S matrix is not unitary as a result. So that is another role of the ghost fields, but on the level of states, the ghost fields have this role of establishing this quartet mechanism and the DRST structure of states. And so I would say the interpretation doesn't need a relationship like this is the antiparticle to the ghost, particle, antiparticle for ghost. Doesn't make sense since they are not particles. They are not to be interpreted as particles. The states, of course, have similar properties as ordinary one-particle states, but they are unphysical by definition. And they violate, for example, the spin statistics theorem, so that would be a spin zero particle. However, a fermion and this combination violates the spin statistics theorem of quantum field theory, which shows that the particle is not physical. And so it's not really right to think of them as particles, only in this formal sense. Structure of states. And so I would say the interpretation doesn't need a relationship like this is the antiparticle to the ghost, particle, antiparticle for ghost. Doesn't make sense since they are not particles. They are not to be interpreted as particles. The states, of course, have similar properties as ordinary one-particle states, but they are unphysical by definition. And they violate, for example, the spin statistics theorem, so that would be a spin zero particle. However, a fermion and this combination violates the spin statistics theorem of quantum field theory, which shows that the particle is not physical. And so it's not really right to think of them as particles, only in this formal sense of Fock space states, as long as you have these unphysical degrees of freedom in your domain.
طبعا في الفيديو السابق رأينا انه على يعني في الفوك سبيس بسبب الكومبينيشن عرفنا انه يعني يمكن هذه الطاقات ان تتجمع وتصبح طاقة ضخمة، بالتالي يتحول الفضاء الى فضاء شبيه بالفضاء داخل الثقب الاسود. بالتالي تقلب المترية الجي ميو نيو تقلب إشارتها، ومن هنا تأتي النورمز. الآن هو يعني يقول أنه هذه الستيت يمكن أن تعدل الإيماجينري بارت وتجعله يعني حقيقيا، وسنرى هذا بعد يعني خلال اليوم أو خلال يوم غد إن شاء الله، إذا يعني ربنا جاب العواقب سليمة ولم تقم حرب وقطعت الإنترنت وما إلى ذلك، سنرى ذلك إن شاء الله. لكن إذا حصل ما نخشاه فسواصل لنا الدراسة وسواصل عمل فيديوهات إلى أن يأتي الإنترنت، وإن شاء الله أنشر في موعده. كتابي سأحاول أن أخلصه بهذه الهيئة. لن أنا حقيقة هناك أشياء كثيرة حاولت أن أضيفها، لكن بما أن السودان انزلق في هذه ال- المعركة المغدور به، يعني هو السودان غدر به وربما يدخل في معركة أخرى. فهذا مع هذه المعركة ربما تؤثر على الإنترنت وتؤثر على يعني حتى مستقبل السودان. و بالتالي سيكون من الصعوبة أن أتواصل معكم تاني. ربنا يجيب العواقب سليمة، وربنا يجنب المؤمنين شر القتال. المهم، ففي كتابي هذا سأختم على هذا الأمر، وسأدون يعني معلومة على أنه أنني ختمت لهذا الأمر لأنه بسبب المستقبل المظلم، وأنه ربما تقوم حرب ويقطع الإنترنت، وبالتالي أفقد فرصتي في نشر هذا الكتاب. عموما سأحاول المساهرة في هذا الليل إن شاء الله بإذن الله تعالى، إذا ربنا سهل ذلك سأساهر في هذا الليل حتى أنتهي من هذا الجزء من الفيديو، وأنتهي من الكتاب إن شاء الله في حدود الغد الصباح أكون قد نشرت الكتاب إن شاء الله، وسيكون بين أيديكم بإذن الله تعالى. عموما يعني هناك معلومات طبعا أضفتها من هذه المحاضرة التي السابقة. أضفت معلومات في هذا الكتاب مثل النورمز، ومثل الفيلوسيتيز، ومثل النورم. لم أكن أعلمها النورم، أعلم النورم نيجاتيف، لكن لم أعلم أنه يرتبط بالمترية جي ميو. أضفت أيضا بصحة المعلومات الخاصة بالبوزيتيف ماس التي تعطينا كتل عالية أو كتل موجبة، ولكنها سرعتها عالية جدا. كنت أظن الموضوع عكس تماما، أنه تعطينا جسيمات لا كتل لها، وكتل يعني مفرقة بين فيها كتل وما فيها كتل، اللي هو السيمتري بريك الذي يحصل. المهم، فهذا ما ضفته إن شاء الله خلال اليوم. خلال هذا الليل إن شاء الله انتهي من الكتاب، وسأنشر هذا الفيديو الليل إن شاء الله، لأنه سأضيفه كرابط في كتاب إن شاء الله. لهذا سأنشره، وإن شاء الله خلال يوم سأنتهي من الكتاب بإذن الله خلال الليل، وأنشره بإذن الله تعالى. طيب جميل، تعالوا نواصل.
In many references, in particular in the maybe more distant past, it was often claimed that ghost and anti-ghost behave like particles, antiparticles to each other, or the anti-ghost field is the Hermitian conjugate of the ghost fields, and so on. But this has been abandoned, and therefore it is now sometimes stressed that they are not. And obviously you see from the derivation we don't need that they are the Hermitian conjugates of one another. In contrast, the whole formalism works beautifully. If we say the ghost field is Hermitian, the anti-ghost field is anti-Hermitian, but they are not related to each other, except for by the commutation relations that we work on. Other questions? Okay, let us briefly discuss a repetition of what we already discussed in the context of electrodynamics in the last semester, namely these favorite so-called problems and magical solutions. Which are kind of simpler problems and simple solutions, whereas afterwards we want to discuss the unitarity of the S matrix, which is a little bit more involved. So see also quantum field theory 1b. So abelian QED, abelian theory and Compton scattering. Let's write down the Feynman diagrams for Compton scattering in QED. There are two Feynman diagrams for electron-photon scattering, where the photons couple in this way or in the reversed way. And we want to write down the T matrix element, or the S matrix element, or anyway the scattering amplitude for this process, which has a structure like this. TFI is equal to polarization vectors epsilon mu for the first photon and epsilon nu complex conjugated for the second photon, times some remaining amplitude mu nu coming from the computation of the Feynman diagrams. Let's not write down what this mu nu is, but it is some expression which involves spinors, u bar and u and p slash quantities and so on. Here for the physical Compton scattering process we want physical photons, so the epsilons are physical transverse polarization vectors. And now comes the problem. The question is this scattering amplitude Lorentz invariant or not? And this is a good question which doesn't have an obvious answer, because the physical transverse polarization vectors, they do not behave like ordinary 4 vectors. They do not transform with lambda mu nu Lorentz transformations, but they have a more different, more complicated Lorentz transformation property. And therefore the question is whether the whole expression is the same calculated in every reference frame. So they are not Lorentz covariant. So the question is the whole expression Lorentz covariant? And what is the answer? We did it in QED last semester. The answer is, of course, yes, the whole expression is Lorentz invariant. And why is that? Because the difference from a Lorentz covariant expression is proportional to the momenta k mu, k1 or k2. The deviation from the correct behavior is proportional to k mu, and the amplitude mu nu satisfies a Watt identity such that its contraction with the case gives 0. And that is why the non-Lorentz covariant terms drop out, and the full result is Lorentz invariant. So that is the problem and the magical solution, namely there just happens to be a Watt identity which we have proven, which is k1 mu times mu nu is 0, and that is also k2 mu times mu nu. So whenever you replace an epsilon by the corresponding momentum, you get 0. And because of that, the non-Lorentz covariant terms drop out, and the TFI is Lorentz invariant. That is nice problem and a magical solution. And the technical ingredient in this magical solution is a Watt identity. Watt identity stands for this relationship, which one can prove by explicit observation. Now, next question. What happens in the non-abelian case? Let's do QCD Compton scattering. QCD Compton scattering. You have, of course, the same Feynman rules as in QED, but there are additional Feynman rules. Does anybody know an additional Feynman diagram which contributes to the process quark-gluon scattering in QCD? Here the quark is a mediator. The gluon is a mediator. How could the diagram then look like? Okay, but if we have here a gluon, then you have a vertex quark, gluon, gluon. that vertex doesn't exist. The spinor line must always be conserved. Spin 1/2 must be conserved. So there is not a vertex, one quark and two gluons, but there are some other QCD vertices. Yep. Additional gluons, but then it would be a different process. So we want to look at this process with exactly this initial and this final state. So the final and initial state should not be changed, but I claim that there is a third Feynman diagram which is specific to non-abelian gauge theories with the same initial and final states. Yes, that's it. So like this. Then you have here a triple gluon vertex, and here a normal vertex quark quark gluon, right? And then you might say this is maybe S channel, that is U channel, and this is T channel or something. Indeed. So that is the third diagram. And you did it with Matthias last week. This vertex here has a horrendously complicated Feynman rule with 6 terms involving all the 3 momenta of the attached gluons. And now the question repeats itself. Is the matrix element for this Lorentz invariant? So the matrix element would look again like that. You would have epsilons for the transverse polarizations, which are not Lorentz covariant. They will be multiplied with some mu nu, but for the mu nu there is a third Feynman diagram which contributes. And the question is the whole result Lorentz invariant? And so you could ask, does the mu nu still satisfy this Ward identity? If yes, then of course the result is again Lorentz invariant. So what do you think? Any guesses? Okay, so this will be an exercise. So you can then check what happens for yourself. And the situation is quite a bit more complicated. Okay, next thing, QED or QCD, that is now the same, scattering for fermions. So let's do this. Just this process, fermion antifermion goes into fermion antifermion. There is just a single Feynman diagram regardless whether you have QED or QCD. And the structure is the following. So I times TFI, if you really write down the Feynman rules, then you have here a gluon or photon propagator, and the value of the gluon or photon propagator is the following: minus I over Q squared times the numerator, and in general the numerator is gauge dependent. So then we have here G mu nu minus Q mu Q nu divided by Q square plus Q mu Q nu divided by Q square times Xi times something else, and let's say here the something else is just dot 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 with overall a Lorentz index mu. So let's call this thing J mu as an abbreviation, like a current. So anyway, something which is contracted with this Lorentz index coming from the gluon or photon propagator, and this could be the expression corresponding to that fermion line or to the other fermion line. So, and it goes on. Okay, So here the gluon propagator depends on the gauge fixing. Question: does the physical result for this scattering amplitude also depend on the gauge fixing, or does the gauge fixing somehow drop out of the calculation? If it were depending on the gauge fixing parameter, that would be odd, because we do not know how to measure the gauge fixing parameter, so it shouldn't be a physical parameter of the theory. It is only an artifact that we introduced in order to temporarily define a quantum theory, but it shouldn't be a physical parameter. So, question: does it drop out? So, the problem is, or the question, is the physical scattering amplitude depending on psi? And the answer is, we did it also in quantum field theory 1. So the psi-dependent terms are longitudinal. They are proportional to the gluon or photon momentum. So all the psi-dependence happens in a way that you obtain something proportional to a contraction of the gluon momentum times the current J mu, which couples to the gluon. So you get this contraction of the gluon momentum times such an expression corresponding to such a fermion line, for example, J mu. And we looked at this in QED, and the QCD calculation is identical. This result is simply 0 here. So it would be something like that, Q mu contracted with a spinor U bar of P prime times a gamma matrix gamma mu times U of P. And Q is exactly the difference between P prime and P, and then you can do a simplification such that you get a difference of 2 terms which are equal. M minus M gives 0. So because of that, TFI is actually psi independent. So, and this is again something like a Watt identity. Namely, such a building block of a Feynman diagram satisfies a relationship. If you contract with a gluon momentum, you get 0. Similarly here, this is a Watt identity where some expression contracted with a photon momentum gives 0. These are identities coming from gauge invariance of the classical theory. So here the gauge fixing parameter drops out. And then we have a physical interpretation of the S matrix. All right, so these are simple problems and simple solutions.
طبعا هنا يمكن أن نقول أن على الجيج فيكسين اللي هو الجيج ديبندنس الجيج فيكسين ديبندنس دروب اوت. لماذا؟ لأنه في النهاية كما ذكرنا أنه الجيج فيكسين يجعل في هناك ستيت يعني ليست حقيقية. هذه الستيت لديها خاصية أنها تتجمع فيها على الطاقات العالية، والفضاء ثنائي الأبعاد يستطيع تفريغ الطاقات العالية هذه، وبالتالي نحن لا ننظر ولا نستطيع أن ننظر إذا كانت هذه الستيت غير حقيقية مثل ستيت S ولا ستيت L يعني تغير شيء في التفاعل. لكن يمكن أن تتبع هذا الأمر في المفاعلات. يمكن تتبع أن نصمم تجربة تتبع الستيت L والستيت S التي تعتبر غير حقيقية، ونتتبعها إلى أن نعرف أي فروقات بينها وبين الوضع العادي. وهذا التتبع يتم عن طريق ماذا؟ عن طريق الطاقات العالية، لأنه ذكرت أنه يحصل كومبينيشنز بين الستيتس وبين المومنتومز في هذه الستيتس التي هي تعتبر انفيزيكال، وهذه الطاقات العالية تفاجأ بها فضاء ثنائي الأبعاد غير المتناظر، لكن في النهاية يستطيع أن يبددها. هذا التبديد، الفرق بين هذه المدة بين أنه يبددها وبين أن تتغلب بدأت يعني الفرق بين المدة الزمنية بين أنها تبدأ وأنه يبددها تخرج ظواهر غير معروفة، مثلا السرعات أعلى من سرعة الضوء، كمية ضخمة من الجسيمات، لأنه كمية ضخمة من الجسيمات يعني طاقات عالية جدا تم تبديدها ولكنها خرجت في الفضاء غير متفاعل. هذه الطاقة العالية تحللت مباشرة، يعني طبعا سرعتها عالية، طاقة عالية، سرعتها طاقة مكثفة وعالية وسرعتها عالية، وتحللت مباشرة تعطينا أجسام أو جسيمات غير متناظرة وكثيرة، كمية ضخمة. يعني إذا زادت كمية الجسيمات من المعتاد، فهذا يعني مباشرة أن هنالك شيء من هذا القبيل حصل. يعني احنا معتادين أنه هذا التفاعل يعطينا مثلا كذا جسيم في الثانية. طيب أفرض أنه الجسيم زاد بمقدار الضعفين، هذا يعني أن الستيت الريال أو الفيزيكال ستيت اللي هو ال والإس عملت مفعولها وأعطتنا هذه الكميات الضخمة من الجسيمات. يعني احنا يمكن أن نقيم تجارب بهذا الأمر.
Obviously, the solutions are and the problems are formulated here at tree level, at the level of very simple lowest order Feynman diagrams. But I give you an illustration of what problems in principle exist and how you can solve them in principle. So you could generalize this and ask yourself, for any S matrix element that you calculate at arbitrarily high loop order, are scattering matrices Lorentz invariant, and then you would need to prove such properties at all orders. And similarly, are physical S matrix elements independent of the gauge fixing parameter, and again you would need to prove such relationships at all orders. So for this interpretation of the full theory, then establishing such identities at all loop orders is a crucial thing. But the ingredients and the outcomes that you would like to have are very well illustrated by these simple examples, and so you can imagine now, first of all, that it can work, how it can work, and what are in general the ingredients. But it's already important enough to know that it works at T level, which is of course very important. But now let us come to the real thing of today's lecture, namely the unitarity of the physical S matrix, which also explains a bit more the role of the ghost field. And I think I organized it such that this morning we will just do an overview of what the question is and some general interesting relationships, and in the afternoon we will finish the topic. And then also do something else because it will not take extremely long. So we start with the S operator. So the operator corresponding to the S matrix, and the S operator can be written as an operator is equal to the unit operator plus I times a T operator, and then this TFI would be a matrix elements of that T operator. And it is nice to split it in this way because there is of course the possibility for no scattering at all, which would be described by the identity, and therefore T is the really interesting physical effect from scattering. Then the S operator should be unitary, and unitarity means the equation S dagger S equal the unit operator, and that is of course now equivalent to some relationship for the T operator, namely S dagger S is now T dagger T plus some linear terms in T plus the unit operator that should be equal to the unit operator. So you can solve it. You can cancel the unit operator from the equation, and then on the right hand side you have just minus I times t minus t dagger. So that is the unitarity relation equivalent to this expressed for the t operator. Okay. So, and this relationship is more useful for us because it expresses the unitarity in terms of the really interesting part of the scattering amplitude. Now, generally speaking, I already mentioned the word imaginary parts. Imaginary parts are very important for unitarity discussions, and you can think of this already in terms of complex numbers. Complex numbers which are unitary are simply numbers e to the I alpha, okay, with modulus square equal to 1. So that is a unitary number. A unitary number which is not identical to 1 or minus 1 must have an imaginary part, right? So this is cosine alpha plus I times sine alpha. So if this unitary number is not equal to plus minus 1, it must have an imaginary part which is non-zero. And how large is the imaginary part depends obviously on the real part. There is a relationship between the real and imaginary part. I'm saying something trivial here. But the same is true for a unitary operator. If you have a unitary operator, its imaginary part cannot be anything. It must be related to the real part, and that is exactly the relationship. So here, for example, the counterpart to this t would be, let's say, 1 minus cosine alpha. If you know 1 minus cosine alpha, you can predict sine alpha. That is exactly the same thing here. So if you know t dagger t, you can predict something about the imaginary part of t. That is the essence of this. And so this is the general unitarity relation. And there is a corollary of this, which is the optical theorem. And very often it is sufficient to just look at the optical theorem, which basically corresponds to that general equation by taking a matrix element, namely a diagonal I matrix element of the same equation. If you take the matrix element of two states, I stands for initial state, let's say in a scattering, take the matrix element of this operator equation with two equal states, I and I, operator or scalar product from the left and right, with some equal states. Let me maybe draw it on the blackboard such that you see what I mean. So I do this here, I matrix element, and also here I matrix element. But what do I get then in more explicit form? I get the following. I get a sum over f of the matrix element tfi absolute value square, because the matrix element can now be written in matrix form by summing over intermediate states f. I sum over a full basis of my Hilbert space of states, sum over f, and then I get matrix element tfi times tif star, which is the absolute value square of that matrix element. Okay, so that is the left hand side. Simply get a sum of squares of scattering matrix elements. And on the right hand side here, by taking this matrix element, I get the matrix element tii minus t star ii. T minus t star is the imaginary part of t. And that minus I drops out. I simply get here 2 times the imaginary part of tii. So I get a relationship between the imaginary part of a complex scattering amplitude and squares of complex scattering amplitudes. It's an interesting quantum mechanical relationship, because, as you know, quantum mechanics talks always about probability amplitudes, and the probabilities are squares of probability amplitudes. And here you have a relationship between squares of probability amplitudes, in other words, real measurable probabilities, and imaginary parts of probability amplitudes. So it is an unusual relationship coming from unitarity. We can visualize it a little bit with pseudo diagrams. So the left hand side corresponds to this sort of thing. You have here an initial state I, and then arbitrary final states F, symbolized like this, some initial state which is fixed, and then an arbitrary set of final states. This gives an amplitude, and you take the absolute square of all these amplitudes. And on the right hand side you have an initial state, then some arbitrary non-trivial interactions, and at the end you again have the same initial state as you started with, and you take the amplitude. So you have a relationship between squares of such Feynman diagrams where E goes to anything, and Feynman diagrams where I goes to I with anything in between. That is the optical theorem. And so here you see something which is proportional to a total probability. The total probability of I going into any arbitrary final state F. That is exactly what you would call a total probability of I scattering into anything. Whereas this is a scattering amplitude, the imaginary part thereof, and it is a special scattering amplitude, namely the forward scattering amplitude, where nothing happens. So this is what the optical theorem tells us. And it is a corollary of the unitarity of the S matrix. Now some remarks about unitarity and this optical theorem. First of all, the unitarity of the S operator holds by construction. In particular, in the operator formalism, it is kind of obvious because the S operator is given by the exponential e to the I times integral over the Lagrangian density. And the Lagrangian density is Hermitian. At least we consider only theories with Hermitian Lagrangian. And then the S operator defined by the exponential is automatically unitary. So this unitarity relationship is true. It is guaranteed to be valid in the theory, but it
طبعا هنا اليونيتاريتي لماذا يعني طلعت حقيقية وفالid؟ لأنه الفضاء ثنائي الأبعاد يفعل آلياته من شرحت ذلك أكثر من مرة، أنه من الآليات التي يفعلها هو تبديد الطاقة. لذا سيعدل هو هذا الفضاء، سيعدل من نفسه، وبحيث أنه يجعل هذه الطاقة هرمشا. يعني يمكن أن نقول رفلي كده، نقول أنه حتى تتوزع جميع الاتجاهات. مثلا بالرغم من أنه عند الطاقات العالية تعطينا زوايا، السكترين يعطينا زوايا ولا يعطينا تبديد في جميع الاتجاهات، لا تعطينا جسيمات خارجة في جميع الاتجاهات. لكن يمكن أن نقول أنه هناك آليات للفضاء ثنائي الأبعاد يعني تفعيلها، يستطيع تفعيلها حتى يجعل هذه العلاقة هرمشا، يجعلها هرمشا. مثلا يكون القطع في الطاقة بطريقة معينة لا يكون عشوائية، بحيث تعطينا جسيمات ذات كتل محددة وذات الإسبين محدد. خاصة الإسبين يلعب دور في هذا الأمر أيضا، يلعب دورا كبيرا في الخروج بعد أن يخرج من التفاعل، لأنه داخل التفاعل الفضاء أيضا داخل التفاعل أيضا الفضاء ثنائي الأبعاد أيضا يغير الإسبين كما رأينا، بحيث أن لا يحصل تفاعل، ولكن بعض المرات يحصل التفاعل بتغيير السبين. وهذا واضح في الآن فيزيكال ستيز ال والاس، يمكن أن نعتبرها هذه طرق تفعل المادة خضاع الفضاء ثنائي الأبعاد، بحيث أنه يظهر فجأة سبين وسبين متفاعلات مع بعضها البعض، ومما يفعل فضاء آلياته بقوة للدفاع النفسي. فالهرميشن طريقة من طرق الفضاء أثناء الأبعاد يحاول أن يجعل كل الأوبزرفبل diagonalize من أجل أن يعني يستطيع يبدد كمية أكبر من الطاقة المكثفة في المنطقة.
Applies to the full S matrix, including unphysical states. So the Lagrangian contains the unphysical fields. It is Hermitian if we include everything that it depends on, and if we quantize in the way we just discussed. We have a space of states which has negative and indefinite norm states, but on that space the S operator is guaranteed to satisfy this relationship. So, and let me also write down the physical remark. So the optical theorem generates relationship between the square of lower order diagrams, right, and imaginary parts of higher orders. So at least if you think in terms of perturbation theory, then this equation must be valid order by order in perturbation theory. So if you have here Feynman diagrams with, let's say, 2 powers of the coupling, you square them, you get 4 powers of the coupling. So you get a prediction from calculating Feynman diagrams with 2 powers of the coupling. You square them, then you know what is the imaginary part of Feynman diagrams with 4 powers of the coupling. So you get relationships of lower orders squared and the imaginary part of higher orders. That implies, for example, you calculate at tree level, you calculate something at tree level, you square the tree-level Feynman diagrams, you get a fixed answer. Then you can predict what must be the imaginary part of loop diagrams. And the optical theorem then tells you what must be the imaginary part of loop diagrams, and if you happen to calculate loop diagrams in some form or some way, and the imaginary part comes out differently, then you have destroyed the unitarity of the S operator. That is the meaning of this relationship. Now the question is, what happens if you restrict your S operator onto the physical space, onto our equivalence classes on this H physical space of positive norm states? Is it still unitary just on the physical subspace? Is S restricted on H physical still unitary? And that is equivalent to saying the following. If you have here the sum over all possible final states, can you, instead of summing over all possible final states in the full space, can you just sum over all the physical final states? Does that already give the same result as the summation over all final states? So that would mean the total probability of physical final states is equal to 1 for any scattering. That is really the question. So you start with some physical state, you scatter, and you get some distribution of final states, and thus the sum of all physical final states add up to 1. That is the question, and the answer is not obvious. The answer is only obvious if we sum over all states, including the unphysical ones, and that is our discussion for this afternoon. We will answer this question. Of course, the answer is yes, and the reason is again word identities and generalized word identities, so-called Slavnov-Taylor identities, which lead to similar relationships as the ones that we see here on the upper blackboard. And because of those relationships, you will see that in the summation all the unphysical stuff cancels among itself, such that the equation here is already correct if you sum just over the physical final states instead of overall final states. And so what we need to do is to establish exactly this cancellation between the unphysical states among themselves. And we do it again like here for the simplest case, for a three-level Feynman diagram, which is already non-trivial, but we will do it, and this will again illustrate for you what would be the general question and some idea on methods how you would tackle the general case at higher orders. Okay, so see you in the afternoon.
طيب جميل. كده نحن انتهينا من التسجيل الثاني، نفس المحاضرة طبعا. التسجيل الأول كان الفيديو الأول كان للجزء الأول من المحاضرة، وهذا الفيديو الثاني للجزء الآخر، وأخذ معنا 45 دقيقة. فهذه هي المحاضرة. اتفاقات واختلافات، لا أعتقد أن هناك اختلافات، لكن اتفاقات كثيرة الحمد لله بين نظرية وبين بين هذه النظرية. عموما يعني إن شاء الله سأجعل هذه المحاضرة أيضا في الرابط كأحد الروابط الكتاب القادم، حلقة 55، وإن شاء الله أقرأ الكتاب وتعال المحاضرة. نفس المعلومات في الكتاب تجدونها في المحاضرة، ولكن المحاضرة هي طبعا أجمل وأفضل لأنه فيها شرح أوفى. الكتاب هو اختصار لهذه المحاضرة، هذه المحاضرات يعني، فالمحاضرات فيها شرح أوفى. السلام عليكم ورحمة الله.